All right, guys, starting some probability today, basic concepts of it. And I'm going to be honest, this video has quite a few slides, and at the beginning, it's going to seem like I'm reading a lot to you, which I kind of am, but hang in there, and the problems kind of come towards the end. Not difficult today, but you really need to understand some of these concepts. First one is huge. Wish I could just drill this in right into your head. It says rare event rule for inferential statistics. We're going to be doing this rule so much. It says under a given assumption, the probability of a particular observed event is extremely small, we conclude that this assumption is probably not correct. And that's what we're going to do this whole second part of stats. You know, a big part of our year is prove stuff almost by contradiction, by saying, okay, the probability is so small that it could happen. It's probably not going to happen. It's probably not correct. So the assumption is going to be false. We're not actually going to prove something is true as much as we're going to try to assume or prove that something is false because the probability of it happening is so small. Let's look at this problem here. The Genetics and IVF Institute has developed a method of gender selection so that couples could increase the likelihood of having a baby girl. Suppose that 100 couples are use the procedure and results consist of 98 girls, only 2 boys. There are only 2 possible explanations. Explanation 1, it just happened by chance. The gender selection technique is not effective, and the result of 98 girls and 2 boys just occurred by random chance. Number 2, not by chance. The results did not occur by chance, so it appears that their technique is effective. Now, the probability of this happening is the deciding factor. It's extremely small for that to happen by chance. I mean, what are the chances of 100 kids being born, 98 are girls? It's very small. So instead, there'd be a lot of support for the claim that the gender selection technique is effective. So that's what we do in stats, is we reject this kind, the chance argument, and say, okay, the chance of that happening is so small that it must be true that the gender technique is effective. That's where we're going with all this. So we're going to learn how to do probability now so that later we can make statements like that. All right, some very important definitions. An event is any collection of results or outcomes of some procedure or experiment. Simple event is one outcome of an event that cannot be further broken down because it's one outcome. The sample space is all the possible outcomes or all the possible events, all the simple events put together. And I'm going to show you some examples of these. Here's a procedure. If you have a single birth, an example event, well, you get a girl. You know, that's one event. The other event would be you get one boy. The sample space is all the possible outcomes. You can get a boy or a girl. Let's extend it now. Let's say the procedure is 3 births. Well, one example of an event may be 2 boys and 1 girl. And that could happen 3 ways. You could get a BBG, a BGB, or GBB, which are girls, boys, obviously. Now, the sample space, these are all the different ways you can have 3 kids. You can have BBB, BBG, BGB, BGG, GBB, GBG, GGB, or GGG. 8 of them. 8 different ways you can have 3 kids. But hopefully those words make sense. Procedure, an event, and the sample space. Notation. Anytime you see a big capital P, it's going to stand for probability. A, B, or C, usually what they use for specific events. So when you see this notation, P parentheses A, it means the probability of A occurring. 3 approaches to probability. The first one's called relative frequency approximation. And this one, what we do is we conduct or at least observe some procedure and just count the number of times it happened, and we're going to use that for our probability. The number of times it occurred over the number of times that the procedure was repeated. So it's not mathematical as much as you're just watching or conducting an experiment and just counting for yourself and saying, okay, the probability of this happening is this. Let me show you one of these. Oh, first let me show you the second one. The second one's called classical. This is the one we use the math for. It must have equally likely outcomes to use this. So assume that a procedure has n different simple events, and each of those simple events has an equal chance of occurring. That's why they're equally likely. The way you find the probability is the number of ways A can occur over the total number of simple events or also known as the whole sample space. So, and they're going to use S over N a lot. Remember, every time you see the word N in stats or probability, it means a total number. S, a lot of times in probability, would mean number of successes, number of ways that A can occur, or number of successes of A. And the third one is actually subjective, which sounds weird, but what we do is we estimate the probability using knowledge of relevant circumstances. And I'm going to show you a couple of those too, and I'll point out to you why it's subjective and why it has to work that way. Okay, before we get into that, you need to know the law of large numbers. And that just says, as the procedure is repeated again and again, the relative frequency of probability, that's the observed, that's what you're watching happen, of an event tends to approach the actual probability. So the more it happens over and over, the closer it gets to the real probability. You'd be shocked. The more times you flip a coin, the more 50-50 it becomes. Like you may flip a coin 10 times, you may just get like 3 tails out of 10. But by the time you get to 100, you're probably closer to 47, 46 out of 100. You get up to 10,000, you'd be shocked how close to 5,000 you are. So the more you repeat something, the larger the number, the closer you get to the actual probability. It's cool how that happens, and to be honest, casinos make a lot of money based on that law. Okay, I don't know if you can read these or not. There's an example of each one. Relative frequency approach says when trying to determine the probability that an individual car crashes in a year, think about how hard it is to figure out. I can't do that mathematically. So what we do is we examine past results to see what's happened in the past. And for a recent year, the result gave us a probability of 0.048, which is like 4.8% chance, that a particular car would crash in a year. And again, that's based on what's happened in the past. Now, the classical approach, you can actually use math. If you're trying to figure out the probability of winning a grand prize in a lottery by picking 6 numbers, and here's the deal though, every combination has an equal chance of occurring. That's what means you can use classical. And mathematically, we can figure out that chance is that. That's really pretty accurate right there. And we're going to find out how to do that later in chapter 4, but not yet. But you can do that mathematically. And the last one's subjective. Subjective, if you're trying to estimate probability of a passenger dying in a plane crash, that's an estimation. Here's what you know. There are thousands of flights every day. A fatal plane crash is very rare, so the probability is very small. So we're going to guess, a good guess would be about 1 in 10 million. Okay, that's subjective because there's no mathematical proof to it. You can't really do, let's see what's happened in the past. You kind of got to be subjective about it. Okay, let's try a few here. The first one says a recent Harris interactive survey of 1,010 adults showed that 202 of them smoke. So this is the first type. We actually did a little experiment here, similar survey. 202 smoke. So find the probability that a randomly selected adult in the U.S. is a smoker. Well, we would just say it's 202 out of 1,010. That's going to be our estimate. And I believe that reduces down to 0.200. Look at the second one. Assuming that 1,000 subjects is randomly selected, find the probability that the selected subject got a positive test. If you look at what this chart has down here, it's talking about drug tests, and people who use drugs, sometimes they get a positive, sometimes they get a false negative, or you can get a false positive or a true negative. But all this problem is asking us for is the probability that a subject got a positive result. Well, this is the classical one. We know there were 1,000 people who got tested, and 134 of them tested positive. So all we would do is reduce that number, the 134 over 1,000, into a decimal, which about 0.134, actually exactly 0.134. Pretty easy stuff mathematically. All right, when 3 children are born, I'm supposed to say children instead of children. The sample space of the genders is, we did this a minute ago, BBB, BBG, BGB, etc. If boys and girls are equally likely, and to be honest, boys have a little bit higher probability of being born, find the probability of getting 3 children, all the same gender, when 3 children are born. Okay, so my sample space, there are 8 different ways you can have 3 kids, and they're listed up here. Now, our success, or what we're trying to find out, is what's the probability that you get 3 of all the same gender, which means you can get B, B, G, B, or you can get G, G, G. There are 2 ways, so that's 1/4, 1 out of 4 chance. Find the probability that in your next stats class, Mr. Brown wears an Alabama cap to class. Again, that's not math, that's subjective. You kind of got to go, well, he's never worn one before. Probably, wouldn't look too good. Number one, he's a Tennessee fan, so he probably wouldn't wear an Alabama cap, so they're probably just very, very low. So we'll say it's probably about 0.0000, like 1/1,000,000th or maybe 100,000th, something really, really small. But again, that's a subjective one. Just kind of say, well, probably won't happen. Same thing here. What is the probability that you'll get stuck in the next elevator that you ride? And again, think about how many times you ride an elevator and how many times from your experience you get stuck. Very small. So that would be kind of like me wearing an Alabama cap. I'd probably go again, something like that. Probably a better chance of getting stuck in an elevator, to be honest with you, than me wearing an Alabama cap, but you never know. Okay, a couple more. We're almost there. In a study of U.S. paper currency, bills from 17 large cities were analyzed for the presence of cocaine. That's kind of scary. Here are the results. 23 of the bills were not tainted by cocaine, and 211 were tainted by cocaine. That's even more scary. Based on these results, if a bill is randomly selected, find the probability that it's tainted by cocaine. And all we have to go by is what we have here. So we had a total of 23 plus 211, so there's 234 bills altogether, and it said if a bill is randomly selected, what's probably that is tainted? Well, 211 were tainted, so that's your probability. If you did decide, you were to turn that to a decimal, it'd be 0.902. So that is crazy. 90% of the bills have some sort of taint of cocaine on them. Who knows why? Don't really want to know why. Okay, a simulation. Simulations is just a process that behaves in the same way as the procedure itself so that you can get similar results. And we do simulations because it is very difficult sometimes to perform mathematical calculations because they're so complicated to get exact probabilities. So what we do, we use the law of large numbers and we simulate the same process over and over and over again. And what that does is it gets us really close to the actual probability. And I used an example down here, like chances of winning a game of solitaire. That's a hard calculation because it depends on what hand you start with. It depends on what cards are on which stacks and things like that. So what we do instead of trying to do the actual math calculations is we do simulations on hands. It's like, okay, how many games you played, do a large number of game simulations. Okay, how many games were won? And then we do the probability that way instead of actually doing the mathematical calculations because they're so difficult. Okay, real quick, we're there. If a year is selected at random, find the probability that Thanksgiving Day in the U.S. will be A, on a Wednesday, or B, on a Thursday. I think you know by now, Thanksgiving's always on a Thursday, so the probability that it falls on Wednesday is 0. The probability that it falls on Thursday, it's got to happen, so the probability would be 1. That is the highest probability that exists. That is the lowest probability that exists, 0 and 1. All probabilities fall between 0 and 1. This is the last slide finally. This chart right here shows you just that. Impossible events, probability of 0. Certain events, probability of 1. The closer the number is to 1, the more likely it is to happen. Right in the middle, 50-50 chance, 0.5. The closer it is to 0, the more unlikely the event is to happen. All right, that was quite a video. Lots of info. I hope it makes some sense. Again, I say this a lot, but I'm more interested in you understanding right now the concept behind the probability. The problems are really easy. There's not much math to them yet. That's coming though, so be ready. But mainly understand what's going on. So I'll see you tomorrow and we'll work on some of this. See you, bye.